Someone is praying for you. Someone is praying for you. So when it seems you're all alone and your heart will break in two.
Welcome to our lessons on ordinary differential equations. In this lesson, we are going to take a look at Wronskian and the linear independence. So let's consider the second order homogeneous differential equation of this form. If you assume that the functions y1 and y2 are two solutions to the differential equation, and so their linear combination is also a solution, then we have y of x equals c1 y1 plus c2 y2. Now, in order to find the constant C1 and C2, we substitute the initial conditions into the equation here. That's these initial conditions into the equation, and then we find our C1 and C2. Now, this gives a system of two equations as the C1 y1 of 0 plus C2 y2 of 0 equals A, and C1 y1 prime of 0, C2 y2 prime of 0 equals B. This is because the second condition is a derivative. That's why we have the y prime here. Now, this is similar to system of linear equations. So, the system has two unique solutions. If the determinant of the coefficient matrix is non-zero, that is, if this determinant here is not equal to 0, then we're going to say that this system here, system 3 here, has unique solution. Now, the determinant, which is this equation, this determinant is what we call the Wronskian of the two functions y1 and y2. So this is what we call the Wronskian. The Wronskian to the two functions y1 and y2, which is denoted by w of y1 y2, is defined by the determinant of y1 y2 and y1 prime y2 prime. So similarly, if we have three functions, then the Wronskian is given by the determinant of y1, y2, y3, y1 prime, y2 prime, y3 prime, and y1 prime prime, y2 prime prime, and y3 prime prime. So if you check the order, you realize that when you have two functions, to find a determinant of a matrix, you need a square matrix. So if you pick it in order, we can see that y1, y2, and their derivatives. But if you pick a 3 by 3, three functions, they need to get a 3 by 3, so you have to differentiate it twice. So y1, y2, y3, first derivative for all of them, and the second derivative. So it continues like that. So if you have 4, and it goes on and on and on. So let's use this idea and compute the Wronskian of these two functions. So the functions are y1 equals to 1, and y2 equal to e raised to the power negative 2. So we are saying that the Wronskian of y1 and y2, which is equal to the derivative first the function 1 and e raised to the power negative t. And when you differentiate 1, you get 0. When you differentiate e raised to the power negative t, you get negative e raised to the power negative t. And the determinant of this time this minus this time that. This time this is negative e raised to the power negative t, and 0 time this is 0. So the Wronskian for this function is negative e raised to the power negative t. Let's take this second example. The Wronskian of this function y1, y2, and y3 is equal to the determinant of sine x, which is the first function, cos x, the second function, and then x squared, which is the third function. If you differentiate sine x, you get cos x. If you differentiate cos x, you get negative sine x. And if you differentiate x squared, you get 2x. Then you now differentiate this once again. If you differentiate cos x, you get negative sine x. And if you differentiate negative sine x, you get negative cos x. And if you differentiate 2x, you get 2. So we take the determinant of this function, and we know how this is computed. You pick the first one, sine x, and you multiply by the determinant of you cross the horizontal and the vertical, you are left with negative sine x, 2x. and then negative cos x 2. Then minus cos x, and the second one, that is the vertical column here goes and the horizontal column here goes. So I left with cos x 2x, negative sine x 2. So cos x 2x, negative sine x and 2. Then plus. Then this one to this column goes and this horizontal goes. So you have x squared multiplied by cos x, negative sine x, and then negative sine x, cos x, negative cos x. So I leave the remaining computation to you. When you do that, you're going to get negative 2 minus x squared. And that is the Wronskian of these three functions. So let's look at the theorem. First theorem says that if the functions y1, y2 are linearly dependent in an interval and their derivatives y1 prime y2 exist in that interval, then the Wronskian of y1 and y2 is identically 0 in that interval. What we are trying to say is that when the two functions are linearly dependent, you're going to get the Wronskian to be 0. In fact, it is similar to having dependent system of linear equations. If you have a system of linear equations, whether 2, 3, 4, a system of equations, and all the equations are dependent system, then the determinant of the coefficient matrix will be 0. So that's the similar issue here. So we are saying that if the two functions are linearly dependent, then their Wronskian is going to give you 0. The second theorem says that if the Wronskian of the function y1 and y2 is not 0 in their interval, then y1 and y2 are linearly independent. That is, if you compute the Wronskian and you don't get 0, then the two functions or three functions or whatever number of functions you compute, they are all linearly independent. Now, I want you to take note of something. For the fact that the Wronskian is 0, does not also mean that the functions are linearly dependent, because you can also have an inconsistent system and their Wronskian will be 0. If you bring it to the system of linear equations, for inconsistent system, the determinant of the coefficient matrix will also be 0. So the same here. If the Wronskian is not 0, then they are linearly independent. But if the Wronskian is not 0, it's not guaranteed. But if they are linearly dependent, the Wronskian will be 0. So you need to take note of these things. So let's pick this example. We want to consider the functions y1 equals to e raised to power x and y2 equals to e raised to power 2x. If you are to compute the Wronskian of these functions, so you are going to say Wronskian of y1, y2 is going to give us e raised to power x, e raised to power 2x. If you differentiate it, the same thing. If you differentiate, you get 2 e raised to power 2x. Now, if you compute the Wronskian, this time this will give you 2 e raised to power 3x minus this time this will give us minus e raised to power 3x. And this is e raised to power 3x. This is not equal to 0. So you can see that these two functions are linearly independent. Let's look at this example 2. Let y1 be equals to x squared and y2 be equals to x times absolute value of x. And they are defined on this interval. We want to compute the Wronskian of y1 and y2. And we want to show that these functions are not linearly dependent. So let's start with the Wronskian. Now, these two functions are not the same because of the interval. We know the y1 is equal to x squared, but the y2, which is x times absolute value of x, is actually a piecewise defined function. So this function is defined by, we know for absolute value of x, it can be x or negative x. So if the function is greater than 0, then the absolute value of x becomes simply x, and this one becomes x squared. So we are saying that this is x squared for the interval from 0 to 1. And if it is less than 0, this should be negated. So that is going to give us negative x squared. That is from negative 1 with 0 not included. This is because the absolute value of x is defined by x if x is greater than 0 and negative x if x is less than 0. Sorry, x is greater than or equal to 0 and negative x if x is less than 0. Some books will define them as x if x is greater than 0, 0 if x is equal to 0, and negative x if x is less than 0. They are all the same. In this case, we combine both the 0 and the x. This one, they are separated. So this is the definition of these two functions. Now the first question is asking you to compute a Wronskian. And for that matter, because this one works on different intervals, we need to compute the Wronskians on different intervals. So from -1 to 0, it means our y1 is x squared, but the y2 becomes negative x squared. So the Wronskian of y1, y2 is going to give us x squared and negative x squared. And this is going to give us, if you differentiate them, you get 2x and negative 2x. And their determinant is this times this, which is negative 2x cubed, minus this will become plus 2x cubed, which is equal to 0. So the Wronskian in this context is 0. Now for the second interval, which is starting from 0 to 1, our y1 is still x squared, but our y2 now becomes positive x squared. So the Wronskian of y1, y2 becomes x squared and x squared, and when you differentiate each of them, you get 2x, 2x, and their determinant is this time this is 2x cubed minus this time that, which is 2x cubed, which is also equal to 0. So since both Wronskians are 0 in the different intervals, we can say that the Wronskian of y1 and y2 is equal to 0 and the entire interval from -1 to 1. So that is the Wronskian. The second part is asking you to show whether these functions are linearly independent or not. And you are going to go through by the same procedure of different intervals starting from -1 to 0. Your y1 is x squared, y2 is negative x squared, and from 0 to 1, with 0 included, your y1 still remains x squared, but the y2 now becomes positive x squared. So we need to compute the linear independence, find the linear independence for both of them, and find C1 and C2. So starting from -1 to 0, you can say you have C1 x squared minus C2 x squared equal to 0. Now in this case, if size C1 and C2 being 0, if C1 is 1 and C2 is also 1, you're also going to get it to be 0. You can check and see. If C1 is 2 and C2 is 2, you get 0. If C1 is -5 and C2 is -5, you get 0. So it means that apart from 0, 0, you have other values that will make it work. Let's see whether we can have the same value. Let's assume you are looking at the first case using these intervals that we have when C1 there. So let's look at the second one, 0 to 1. In this case, you're going to have C1 x squared plus C2 x squared equal to 0. Here, we can see that when C1 is 1 and C2 is -1, you get 0. Now, at every stage, what we are expecting, this is also different for apart from being 0. We can have other C2 when C2 is 2, C1 is 2, and C2 is just -2. You are still going to get 0. But let's pick a comparison here. If you pick this set, when C1 is 1, C2 was 1 in the first interval. But here, when C1 is 1, C2 was -1, and which is not possible. Because there's a constant, and the constant should remain constant wherever you go. So you cannot have C1 to be 1 here, C1 to be 1 here, and then the C2 is 1 and it's -1 here. So that's impossible. So because of that, we can now conclude that it can only be 0 when C1 and C2 are both 0, because the only time when C1 and C2 are the same in both intervals is when both of them are 0. And for that reason, we say that only C1 being 0 and only C2 being 0 will have to make this linear combination 0. And therefore, we can say that the functions are linearly independent. So if you go back to our theorem, it says that when the Wronskian is 0, then the functions are not linearly independent. But this one says that even though the Wronskian is 0, the functions are linearly independent. And that is why we are saying that for the fact that the Wronskian is 0 does not necessarily mean that the functions are linearly dependent. It can always be linearly independent, as we have seen from this exercise.